Okay, so operating system tuning, as they say it. Okay, now earlier, from a system administrative perspective, the way the way all this was done is it was systems admin's job to uh, you know get performance metrics, okay, through various methods, and he himself tunes it. Okay, and he himself tunes it. Now things have changed, right? And it's all gone in a different way. And from from a DevOps perspective, it is now just not the job of a system admin to tune your performance. It is a combination of your system admin as well as your app developer who would sit together and do this. And that is one big change which has happened, which was earlier, it was a very difficult thing to get it done. The developers wouldn't come by to do this. Now it's done together. And if you don't do this together, specifically in organizations which are internet facing, right? I mean, when I say internet organizations, they will never survive, and it is a continuous struggle. And as an operator, it's a continuous struggle to put all this in place. You wouldn't know where how the performance is kind of degrading and why it is degrading. There could be various reasons which get into this thing. But anyway, so we will learn our basics to understand how we would start gathering statistics and one component. Now we saw that we have learned about infrastructure. So the infrastructure automation layer, we learned about config management, configuration automation, and then we also know there is CI/CD layer, right? And the other fourth important component in this layer is your monitoring. Okay, it is the monitoring layer, which when I say monitoring, it is not only monitoring, it is alerting. So that means there is an event management happening. And if you remember some time back, I talked about this e-com companies way of them starting this whole new VM when some event occurs. Okay, so that all happens through this monitoring aspect of your performance. Okay, now what I have noticed, the big difference between enterprise world and the internet world is, internet world uses highly customized monitoring tools, highly customized monitoring. They do not use any of the tools which are available in the market, either from an IBM's Tivoli series or HP's own OpenView series or BMC products. None of them use these branded products. They all have a customized solution. Some even building their own monitoring tools. Okay, some building even their own monitoring tools as such. Okay, so that is how it's different. And why? And what is so important is, if you look in an enterprise world, the monitoring tools are so disorganized and so disconnected. You don't see that synergy which you are supposed to see. Like I gave you that example, right? If my present application can handle 100 users, and if the 101 user come, is not able to handle, but the monitoring system should immediately recognize this, trigger an alert, and that alert should be to go and tell your backend system, please create a new VM, right? That is going through your, when I say create a new VM, it's most likely through, how do you do it? Will you go do an install? We don't, right? We do cloning. And how do you do this cloning? And we clone through this configuration management systems like Puppet and Check. So we clone it, we apply our configs. Now you know what when I say what do you mean by applying configs, right? After yesterday's session, we apply these configs, install your application, and you see all that how that we saw how it installed the app, right? Like Apache and all that. We install it, we start it, and of course there are other tools, other things which we saw when we learned Nginx, that we need to connect a web server to Nginx, right? To as a part of the load balancer, and we need to do the changes. And how do you do the changes? Again, nothing manual. Everything will be automated through your config management tools. Okay, so with all these in place, you have such a high synergized system, and that is where all these big five Excel, your LinkedIn's, your Amazon's, Google's, Yahoo's, and Facebook, they have such highly energized, synergized system that everything is integrated. Your infrastructure automation layer, your what is it? Your configuration management, your CI/CD, and as I said, there is always another layer. You know, the application deployment layer. Some use, some may not use, because I said that can still be integrated back into your config layer. So most people are still today using your config as your deployment tool itself. Okay. Now all of this plus your monitoring. That's it, and that is DevOps. So if you know all this, plus you know, I think our next class is going to be learning about a language. You know one of the languages, either Perl, Python, or Ruby. And today, as I said, it's all about knowing Ruby and Python more specifically. You have the complete set of skills to go about doing it. Okay, so let's go ahead. Now, what do you monitor in a system? Okay, what do you monitor in a system? First, you monitor your 4 subsystems. Okay, your CPU, your network, your I/O, and memory. Right? These are the 4 subsystems you monitor. And another thing which you monitor is apart from these four physical tools, is your operating system related parameters, which will, of course, indirectly affect these 4 subsystems. Basically, you're monitoring these 4 subsystems. Okay, and how are you monitoring them? When I say monitoring, it's monitoring through your operating system, and operating system has the device. Okay, see, I'll give you a basic example of how. See, it's very easy today. Or I won't say easy. See, today, I can have any kind of hardware. Okay, I'll give you a very classic example, which how the software and hardware behave so differently. See, today we have a lot of these scanning applications, right? Which they use in medical world. Whatever kind of scanning, any kind of scanning. Now, these scanning data, what you get, are in a raw format. Actually, it's a raw format. See, example. Imagine you are using ultrasound scanning. Okay, so what are you actually sending? You are sending sound. You are sending some sound pulses, getting that data, and storing it in a computer. Right? It is not creating any image. It's right. It's not creating any image. Now, that is why these medical software professionals are, very big in demand. You actually use this raw data to create that image, and you're literally creating a moving image as well, right? So how do you do this? It is you take this data and then you transform it using a software to create that image. Now what is funny is when you create this software. And so it could be normally it could be a Windows app, a Windows software. It could be a Mac. and I have not though seen much in the Linux world. Okay, so it's these two. The same image, if once you open in Windows, may not be the same image what you open it. So I mean, this is it's a root shock. Okay, but we have seen this happening. A scan image, Doppler, ultrasound scan image, when you open in Mac, it's different to what you see in Windows. And I'm not sure how the doctors manage out these situations, but you get this difference. And why? That's because of the software. Same way, I can have the most powerful hardwares or the best hardwares available, but you don't write your software correctly, right? You have this problem. So if I look at these four subsystems, that is your CPU, network, and memory. So the most important software for these guys are its drivers. The drivers, when I say drivers, it is that piece of software which talks directly to the hardware. Okay, so when we are tuning, we are tuning a lot of those things actually, yeah, very indirectly. Okay, so that's how you would want to start looking at these things. Okay, now CPU tuning. Let's understand what this CPU means. Okay, tuning means is all about. Now, first thing that you should understand in CPU is, we talk so much about parallel processing. Okay, let's take one CPU. One CPU which has just one core. That is talking about CPU like one which would have been probably released in early 2000 and the 90s. Okay, we had only, if I say take a CPU, it's only one core, right? Now, my question is, in that CPU, right? In that CPU, what I want to ask is, how many programs can be run simultaneously? Do anybody have an answer to this? How many programs can be run simultaneously? I have a CPU. Okay, I'm just looking at you can even take today's CPU, but I'm saying it has to be just single core, a single socket. If I take one of it, does anybody know how many processes can I run simultaneously? Any idea? Okay, so I think I can get an answer though. So that but basically telling you at a given point in time. When I say given point in time, it could be a time in nanoseconds, or a time in microseconds, or time in milliseconds. Okay, at any given point in time, I have a absolutely clear. It's only one at a time. Okay, that means at any given point in time, only one process. There is nothing called parallelization. Parallelization is an image created because you execute in less than a second. Okay, when you start seeing programs getting executed in microseconds, you don't feel that difference. Okay, so so the applications are so quickly run through that you're not finding that as if it is going serially. It is never ever parallel. It's always only serial. Okay, so why? Yes. So why I'm saying that is, now these terms are actually related to that. Okay. Now let's say I'm opening my browser. Okay, let's say I'm opening my browser. Now, what does this cost? So first, your operating system is divided into two spaces. If you, I hope you know, you are aware of this. It's called the user space, and you call the kernel space, right? I hope you are aware of this. Why this distinction has been made? The user space and kernel space. So first thing you should understand, any programs running in your kernel space runs very fast. Okay, Why do they run fast? Because they are the software code which can talk directly to the hardware. Okay, so they are the code which run directly to hardware, and whereas user code or the user space code will to talk to the hardware, they will have to go via the a kernel space. They cannot talk to the hardware directly. I think I have a question in. Let me. Yes, yes, dear. Yeah, your kernel space. So every operating system is divided into two parts, right? Your kernel and your user space. So user space is all about what do you get in your user space? You in your user space is where your shell is. The shell, whatever you talk about your shell, your bone shell, cone shell, whatever, or your basic SH shell. Okay, your shell is basically a user space. That is where through which we interact, right? If I take this from the perspective of this is my shell. Okay, and and uh, and below this shell is your kernel. Now, to talk to my kernel, I mean, I don't have a reason to talk to my kernel though. But suppose I want to send a packet. I mean, I want to do a simple application like FTP or an HTTP. What happens? The commands are given here, right? The commands are here. SCP, copy. The commands are given here. This command is taken by your user shell, your user space, and then this user space will then contact the appropriate pieces of code below. When I say below, it contacts the appropriate piece of code in the kernel space to send this to the network, and then from the network card to the other side, right? So that's how this whole thing works. Okay, so there's a user space and there is a kernel space. Now, another important aspect is, see, there is this word called Jiffy. Okay, I don't know whether you're aware of this word. There's this word called Jiffy. So what is Jiffy? Jiffy is the amount of time a kernel allocates to an application to execute. Okay, it's the amount of time which is allocated to an application to execute. Now, when I say you should understand these a few things. I hope you would be aware, right? I'm sure you should be aware of these. What is if I just want to ask how many milliseconds make 1 second? Okay, so you should know this, right? So that's around 1,000 milliseconds make 1 second. Sometimes, I mean, I know we have done all this in the past, but we tend to forget it. Then 1,000 microseconds make 1 millisecond. Okay, and so and 1,000 nanosecond makes 1 micro. 1 micro. So that's how it goes. Now, your CPU works at nanoseconds. The CPU works at nanoseconds. Okay. Whereas, so all these, see, all your, arithmetic logic unit. If you remember, if you know the CPU architecture, there is a CPU, and next to the CPU there is some L1 cache and L2 cache and things like that. So all those work at kind of nanoseconds. So anything beyond that, once you hit your memory, that is main memory, they all work in microseconds. Okay, and for a user, the CPU allocates time in milliseconds. So that means if I want to run an application like a web browser, they give him 200 I think by default, I think it is 200 milliseconds. I think it is by default. They give him 200 milliseconds to execute this application. Now, during this time, if he is not able to execute, he is thrown out of the CPU and put into a waiting queue. And this is called as context switch. Did you get this? Context switch means when a given process, okay, when a given process consumes its given time, and but the process isn't complete because of various reasons, yeah, the CPU the kernel will do is kernel will remove him from the active queue and put him into a waiting queue. Okay, kernel will remove from an active queue and put into a waiting queue, and then he puts in the process which was waiting for to run in the hierarchy. Okay, so this way, and then what he will do, he will bring back the process. Okay, he will bring back the process after the priority processes are run, or whatever was in the queue at that time, it is run. So, but this process of switching, removing an active process from the core of the CPU and placing him in a wait queue is known as context switching. Okay. Now, why context switching is so important? Now, context switching is important because your application can do context switching in many ways. One, if the code is not written properly, it is unnecessarily consuming a lot of CPU time. Maybe you have written a couple of extra loops, which probably is not required, right? So it is consuming a lot more time. Else, what happens in today's world because of a cloud and various other aspects, something else also happens. So let me see. I have a question. Sorry, I think it's the same. I thought. Okay, so because of today's workloads, so you need to actually, one big activity you do as a part of DevOps is you analyze your application. Okay, you will have to analyze your application from a performance perspective, and of course you need to do it with the DevOps to do. So this is also called as profiling, right? It's also called as profiling. I think I did have a question. Yeah, hi Ashwin. Difference between single core, multi-core. Okay. Okay. So how do I show you that? Okay, let me get onto the web. So Ashwin, I'll show you. I'll show it to you. Okay. Okay. Multi-core CPU. Okay, here you go. So, okay, see, this is a Pentium chip. I mean, this is an Intel chip, right? This is an Intel chip. Okay. Now, what do you see? And comparing, if you have worked with the earlier systems, is this single chip, right, is called as a socket. Okay. Today, these are the terms used. That single chip is called a socket. This is a chip which goes on the motherboard. Okay. Now within this chip, then there is the CPU, integrated, and within the CPU, when I say CPU, I can't use this anymore as CPU. Actually, CPU is this, which is called as core. Okay. So today, this this whole thing appears as a CPU to you, they are not. So this is one socket in which this is your CPUs, and each CPU is called as core. So by default today, I think from probably 2014 onwards, or maybe going into 20, you will have one CPU, but by default, or one socket, by default you most likely end up having 4 cores. That means 4 CPUs. Okay, you'll be surprised to know, if you get any of these mobiles, right? These high-end mobiles, which either of these Macs and Sony Ericsson and all those, each of those will have actually 8 CPUs, but that's a different architecture altogether. 8 cores. So this is what is called as a core. Why do you bring in hyperthreading or the CMTs and SMTs? Is the cost involved in context switch is less. Now, what do you mean by cost? Now, if I take one core and my application is running there, once your application consumes that given amount of time, his whole state has to be copied into some location. It could be a L1 cache or an L2 cache or somewhere. It has to be copied, because I told you, right, you need to bring it back for it to run again. Okay, because the process is not complete. It is not in a complete state. Okay, so if you have pipelines, then what happens is, it is just having like multiple queues. If somebody is waiting multiple queues, somebody is waiting to just open out the purse and then give the cash. By the time the counter guy can go to the next guy who's ready with the thing. Okay, and he comes back to the other guy. So the cost involving for context switching reduces if you have multiple pipelines. Okay, and until it's called, as rightly pointed out, it's by here, it is called as hyperthreading. Okay, and each processor, be it IBM, be it Spark, be it your Itanium, each have this technology today to get that. So we can do this. Okay, so I'm running this command called vmstat. Okay, okay, this is interesting. I got what I want also to see. Okay, and this command. Oh, sorry, I missed that. And okay, I wanted to tell you on run queue and utilization. Okay. Okay, so if you see this, this is vmstat. Actually, we are gathering the virtual memory statistics. Okay, but don't get confused by the word that this is also used to do CPU statistics also. Now, in this, if you see the CS means context switching, and if you are seeing, now I need to profile my application to know how much context switch it does. So this can only happen when you do a performance testing along with the thing. At that time, if you gather the statistics, you will know how much roughly does it do context switching. Okay. Now, why do you want to know this? Is if these numbers are very high, that means the CPU is getting clogged or getting not clogged. It is unnecessarily going into too much of wait state without much processing happening. So you need to know your context switching. So context switching is got from this line. Okay, that is one parameter. Run queue. What is this run queue? Okay, so what is this run queue? Run queue means in my active pipeline within the CPU, how many processes are running. Okay, now we said, right, at a given point in time only one process can run. Now if I'm running the second process also, that means here if you see, two processes are active in my CPU. Okay, and let's take a very simple case of only one CPU, one core. Okay, so that means if there are two runnable threads, as they call it, only one is active, so one is waiting. Okay, now in this idle, and if this kind of persists for a long time, that means your CPU is overutilized and you would need to add additional cores. Okay, now how do you know whether you need to add additional cores? That is looking at the second parameter called B. Okay, what does B? So R shows you how many processes are in active queue. I'm sorry, I'm showing you all in Unix because that's been my area, but you can get the same information for Microsoft also. Okay, but I don't know many of those commands on how to get. So okay, so that way runnable threads show you how many runs are in queue. Now if this particular column gives you any number, okay, that means that some process is getting blocked. B means all your blocked process. See, I can have many things running. I mean, that is okay. That means it's running, getting executed, closed. But for some reason, if it's getting blocked, and if you see this over a long period of time, it means that there is some problem with your CPU. Okay, so I hope you understand these terms. Now, context switch, run queue. Okay, and let's look at what CPU utilization means. There are 3 threads, right? This is the utilization. Okay, you could. I don't know whether this command is there. Okay, it isn't installed, so you could actually see that. If not, this will give you 3 parameters. Your user, so you know how much of your application was getting used in the user space, how much of that was getting, how much of your applications were getting used in the kernel space, and how much of idle time it was doing. So when you have too much of idle time and too much of blocked process, so you need to see where it could be getting. So there is too much of correlation, too much of a correlation. If there's a lot of idle time and there are a lot of context switch happening, and you also see blocked parameters, and you also see a lot of runnable things, then you need to come and actually start probing inside as to what may be happening. So I hope you're getting all these parameters in place. Okay, and then there is this load average. So what is load averages? Okay, I forgot that command. Sorry, I sometimes too obvious commands are just forgotten. Oh, sorry, uptime. There you go. Yeah. No, the command is command. See, the load average is uptime. Okay. Yeah, if you don't use some of these for a while, yeah, this is your load average. Okay. What this tells you is, what is the most important parameter here is now if you see the load average for this parameter is for 1 minute, the last 1 minute, the last 5 minutes, and last 15 minutes. Okay, if this load average is high and these parameters are also showing high, that means for by the straightforward assumption there is some block, there is some clogging happening in your CPU, and it may require upgradation, or your application itself could be faulty. Okay, so load average means per core how many processes are running. Now in this case, I think it's just only one core, and I can see 2 of them running. That's okay. I may see even 10 of them running. But when it says the average this should not be integer numbers. That is 2, 3. You can see. I mean, if Ashwin just checks in his Ashwin, if you can just check in your machine, and if some work is happening, your uptime should show averages like 2, 3 and stuff like that. Okay, so when you see numbers in integers for per a given core, you see anything beyond 4. That means in one core we have 4 applications running. So that means the utilization is close to 100% most of the time, which is a situation saying that we have a clogging happen. Okay, so that we need to check it out. Okay, so that said, yeah, as I was speaking, I think yeah, you're right. Your top also should give you that load average, and I overlooked it. Yeah, it's also there in this. I started with it, then I missed it out. Yeah. Okay, so uptime top will give you a load averages. Okay, yeah. So are you kind of clear with this stuff now on how the CPU is? So CPU, how the CPU is monitored. Okay. So I hope you understood on the CPU. So I think as I will just run through these, I hope I've explained this. So when CPU switches from one process to another, it is called as context switch. Okay, when a process switch happens, kernel stores the current state of the CPU in the memory, right? It should always, otherwise I can't retrieve it. Kernel also retrieves the previously stored state from memory and puts it in CPU. Okay, this is what I want to tell you, because of cloud today, cloud, right? In the cloud environment, what happens is, I mean, when I talk about cloud, that means network is utilized high. Okay, and in cloud, we even storage is through network, right? It's all through iSCSI. And if your storage utilization is high, you see lot of context switching, lot of wait times, lot of block storages because of this. So that is why they say whenever you put your application in the cloud, please test it. Having the application, testing an application in an on-premise server and then putting onto a cloud does not behave. So everybody today does a cloud testing of their software, okay, to make sure the performance is in a good state. Okay, so run queue. So run queue indicates that the total number of active processes in the current current queue for the CPU. Okay, so when CPU is ready to execute, it picks up from the run queue based on the priority of the process. Okay? Please note that the processes that are in sleep or IO wait state are not in run queue. Okay, which I told you. All run queue means it's an active queue. Others are put into wait state or other queues, whatever that may be utilized in the thing. Okay, and run queue also indicates the number of processes that CPU is handling and what is the load on the CPU. And CPU utilization. So the first thing, indicator of any performance related problems are your CPU utilization. So CPU utilization indicates how much of CPU is currently getting used, and this is fairly straightforward and can be viewed from a top command or whatever that may be. And 100% means the system is fully loaded. Okay, we know that, and as I said, this needs to be correlated with other parameters like the R field, B field, your upload, your context switches, etc. And another thing which okay, you should also need to know is if you see too much of utilization in the SY column, that is also not good. When I say SY, that means too much of kernel is utilized trying to process a particular user's application. Okay, so you should see more activity in the user space, not so much as in the kernel space. Kernel space high activity means, yeah, there is something amiss there. Okay, so that is what you need to understand as well. Okay, so load average indicates the CPU load over a specific period time. Okay, on Linux, load average is displayed in the last 1, 5, and 15 minutes. This is useful to see the overall load. So a load average of 0.751 indicates the total load on the system in this order. And if it is 2, it shows that two processes where the average number of processes in the last 15 minutes, 2 processes. Okay, so in a single core, 2 is okay, 3 is tolerable, 4 means suspicious. Okay, it depends, but it still depends. You can still see that can be more than 2 eyes also. And how does it become suspicious? Why? See, I don't mind, even 5 processes running in a single core. But what I need to see is all these processes are not getting context switched. That means it's executing and then closing out. But if it's executing and then getting context switch, that indicates there is some problem with your CPU. Okay. So load average is calculated by comparing the total number of processes in queue and the total process in the uninterruptible task status. Okay, so that's how it is calculated internally. Now, what I want to tell you is for monitoring, okay, I said everything will have to get connected to a monitoring system, right? If I look at these big 5 guys, how they normally do is they run basic Unix commands only. Okay, they run these basic Unix commands. I give you a rough architecture on how. If I want to know my load average, what this guy do is he will execute he will run a cron job. Okay, dumping say load averages probably every minute. Okay, he runs it and then he saves this in a local file or something like that, and then these monitoring tools or monitoring servers will connect to these systems and pull these statistics out. He pulls them out, then okay, process. He will use some database. He will store that. So the metrics is collected every 1 minute, right? It's collected over 1 minute over its life cycle, and then we graph this. Okay, so graphing is one of the best ways to visualize our performance parameters. So 2 things you do. One is performance monitoring. Okay, that is statistical gathering. So ideally, I have not seen anybody going beyond using any other than your system commands. You use system commands, you log these data somewhere, and then another process will come and pull these data and then process it and graphs it. And this master server also has the ability to, as I said, if I take it's not only system logs which are getting a kind of a log, right? If I take a web log and I see, and through the web log, I can see that number of users are going up beyond, or number of sessions are gone beyond, or number of transactions beyond. I can do those various things which I talked about, right? Okay, networks. Okay. The first thing which I always love to talk about that. Again, I think let me just check what is it coming. Okay. So networks. Okay. So when we talk about networks, we should understand these terms like what is MTU. Okay. We should understand what is the size of an MTU, what is a session, what is how do you create a session, and how the packets are transferred, then what is these buffers. receive buffer, send buffer, and things like that. Yeah, you need to understand all these aspects. So performance tuning a network today is the most complicated task than anything else, because we do not have too many parameters to do performance tuning of network. I'll tell you, one of the most highly sought after people in the industry is protocol testers for networking. Okay, there are a set of engineers. I know a couple of them who do these testing. See, take this packet, take an MTU packet. Okay, if I take a network packet, imagine the testing that you need to go when it goes under this cable, undersea cable, or even to a satellite. So they probably have the most sophisticated testing tools. And as an engineer, we do not have too many parameters. As systems engineer, we don't have too many parameters also to fine tune, because a network packet, when it's going across multiple routers, these network packets can get sliced or can get split, and then it is further sent. Once it gets split, the performance actually goes down. Okay, so what do we normally do in a network is we set your send buffer and receive buffer. Okay, send buffer and receive buffer to allow for better performance. Okay, now why send buffer and receive buffer? So most of these commands are all netstat based. Okay, I think yeah, I don't recollect most of So okay, so it shows you how many packets it is received. It will show you if there were any errors. Okay, it's like incoming, any package discarded. So you need to see if any of these are, if there is any discarded packets happening. If it's discard happening, it could be various reasons. It could be a switch sometimes going bad, or there is a bad connection between. Okay, so if you you see any failed connection attempts, how many active connection settings, how many passive. These are the statistics which they take. Okay, how many segments were received, how many segments are sent out. All these statistics. Netstat is rather the only command which gives you all those parameters which are coming. Okay, but we use various tools to actually do an analysis, and analyzing network performance has always been the biggest problem. But what the only way for us to tackle, and the only option we have, is to increase or decrease your buffer size. Okay, which can be set in your Unix system, in your etc system. That is one thing which you can actually do. Now, there is there's another interesting thing which is of kind of you might have noticed a lot. Okay, see, this concept is called TCP slow start. Okay, what TCP slow start means is when you establish a connection between you and another network, so anything for that matter. Okay, so let's say I'm going to www.google.com. So we are establishing a connection, right? We are establishing connection. So to establish a connection, there is 3 packets, and SYN, ACK, SYN, and followed by the actual data. Okay, actual data. Now, so when I send my SYN, ACK, SYN, it also advertises. I'm initiating here, right? I initiated this to the Google server, and when I initiated the Google server advertises at this moment what is the size of packet it is willing to accept. Okay, so this is normally multiple times of MTU. Each MTU, that is the default packet size which is sent across your network. Each MTU is around 1500 bytes. Okay, So when I send one packet, it always has to be less than 1500 bytes. So when I'm starting initially, it is normally probably twice or thrice this size of packet it will accept. So once it receives this, the next he will tell increase the size to 4, and in the next send data send, it increases to 5, and it goes on up to a maximum of I think 65,000 something like that. Okay, it goes up to that level. Now what happens is I'm increasing the size of packet for every return journey, right? I had the packet has to go, come back, and then it says, okay, now I can increase. So this is called slow start, slowly sending small units and then sending the larger unit. What people are thinking is, why do we do this slow start? Let me send a packet of 1500 into 5 times in one shot. Doesn't that make sense? So that means if I were to load, so today if you take the index page of any major organization, especially like if I take a Yahoo page, it is kind of reaching 1 MB. Earlier, all your index pages would be like 100K or a 200K. Now we have breached all this. We are reaching actually nearly 1 MB. So if you want to download 1 MB, look at the number of cycles it would have to go through. It is like 1500 divided by so many cycles that we need to go through to get this. So a slow start is a process by which we send small packets and then get in and then go on increasing till you get a bigger packet. Now, where you see a lot of differences when you during the slow start process, imagine I have reached sending the maximum. Okay, now the guy in the Google side says that now you can send me the full bandwidth of your network. So if it's 1 gig, he says, okay, you can send me that 125 mega. I mean, you can't do that much. Okay, you will send in much less than that, but you can utilize my full bandwidth, and so you send that. During this time, if there is by some chance somewhere in some router some clogging happens and this packet has not reached on time, the complete bandwidth is slashed and it goes to a slower state. This is what you see sometimes when you browse, when you connect through a wireless. Since the density, the density of the air changes because of various reasons, you see sometimes your laptops performing slowly because of TCP slow start, your CPU getting clogged, not clogged, going into an idle state because it is waiting for the packet to come. Okay, and everything is put into a wait state because I'm still not received that thing. So that is why sometimes you see your wireless going slow and your cable, the cable is always going fast because I don't see any kind of interference within the network as such. Okay, that's something which I wanted to tell you on the network front. Okay, so as I said, all of these performance errors can all be gathered through a netstat, netstat minus s, that is socket. It gives you all kind of parameters if there are any errors, how many packets were dropped, and various things can be actually gathered through this particular parameter, and then we take a decision according to that. It could be various reasons, we can't tell why it could be. So as I said, it could be a faulty adapter, or it could be so many things. But we will look at, we ideally start with this to look at what might have gone wrong. Okay. IO. Okay. So IO as we all know, is the slowest component of your CPU. And as they always say, how strong, when you look at a chain, how strong is your chain? The strain is as strong as your weakest link, right? So in that sense, if I take how fast is your system, it is as fast as your disk is, right? So that is one activity which should be checked at. Okay, so now looking at disk, the standard command is iostat. Okay. This is okay. This is a little more nicer, right? Way of looking at it. So iostat is one single command which gives you all parameters related to your disk. Okay. So let's go through and understand a little bit on the disk side. Okay. So people use this term called IOPS. Okay, people use this word called IOPS. So they will ask you, how many IOPS can your disk support? Okay, so today the fastest disk that you get in the market is a SAS drive, 15,000 RPM. Okay, so if you look at what IOPS supports, it roughly supports anywhere between 180 to 200. Now, if you ask me what is IOPS, IOPS is nothing but these two fields, reads per second, writes per second, adding together gives you the maximum number of IOPS. Okay, here we hardly have any thing because the system is not utilized much, right? So that's why we are not seeing anything much. Okay, so what is IOPS? IOPS means reads per second plus writes per second. Okay, and how do you get these details? You can get it from here, back of your disk, or any parameter, or parameter if you know the particular product type, you can get that. Okay, so IOPS indicates how many transactions I can do in a disk in 1 second. When I say 180 IOPS means I can only do 180 transactions. That is the meaning of it. Okay, now I know disk says that my transfer speeds are in megabytes. I understand that. Okay, but that when I say transfer speeds are in megabytes, now what happens is you have to look at your application in two formats, okay, or two profiles. Does your transactions do throughput based? Okay, whether it is it a throughput based application or a random application? Okay, so what do you mean by random application? Reading data from a database, it is random. Why? Because I may be reading in the one time I may be reading in my first line, and then I go back and read in my last line. Okay, so this is a random activity. That means my disk head should go up and down across the tracks to find out my data, and that is why it is only able to give you 180 or 200. So IOPS is associated with applications which are random. Okay, so understand this. IOPS is associated with applications which are random. So that means if my database is installed on my disk, and then I say my IOPS is 200, that means it can only do 200 combination 200 times a combination of read and write in a second. Okay, it can't go beyond that if it's doing random. Now, that is when you say your applications are what do you say, these random when these random reads and write happen. Okay. Now, if your applications are throughput-based application, so throughput-based application means an application like listening or streaming audio, streaming a video. Here, what happens? Here, I don't look at my application in terms of IOPS. Here, I look at transfer speeds. Okay, so where do you see that? Okay, so if you see TPS, okay, transfer speeds. Okay, you see. Here you say in 1 second, how much of data, how much of your data gets transferred. Okay, so you have to profile your application into any of these two categories. Okay, either the throughput mode or the random mode. Okay, so once you know how your application behaves, whether it's throughput or thing, once you know that, you will be able to then understand how your applications are going to be utilized. Because what is important is when you are sizing your database, you should know how this particular application, how many reads it will do or how many writes it will do. Okay, so based on that, I need to I'm not going to use one disk, right? I'm going to use multiple disks. So if my application says that I need what do you say a 500 IOPS for this application, how do I get it? I can't get it from one disk. I need to add 3 disks, right? 200 plus 200 plus 200 to get that 500 IOPS per second. Okay, now you have created those 3 disks. Now you know adding disk also means a risk in terms of failure, right? So I need to mirror them out. So and it goes on that way. That's how you kind of design your your applications as such. Okay. So this said, what do you look from a disk perspective is okay. You see, what you need to see here is what is the average service time per disk. Okay, your average service time per disk should ideally be less than 3 milliseconds if my disk is local to my system. That means it should be attached to my system or your direct attached storages. DAS. If your storages, if your disks are either a NAS based or a SAN based, we should ideally still have this processing. The average service time, okay, this average your service time should still be less than 9 milliseconds. Okay, that is the standard acceptable time. Anything beyond this means we are introducing IO bottlenecks. Now, when you start getting IO bottlenecks, this is where you start fine-tuning your file system. When I say fine-tuning file system means, it basically means adding more memory and having more of the data in the cache. That's the only way out. Okay, at this moment, that is the only way out. But all this is changing with the coming of SSDs, your solid state devices. What we have today is only HDDs, right? Your hard disk drives. Okay, so SSDs. Now, what did I tell you about IOPS? Okay, IOPS, I said in a HDD is nothing. Maximum is like kind of 200 or 230 if you can maximum squeeze out. That's all. But in an SSD, this goes to 3000. Okay, so if you use SSD disks, this is the random read-write performance I can get. Okay, and that is why today many people are going towards SSDs, but the cost is still a factor, but it's come down. And I can tell you one major change which has happened recently. The entire Amazon servers have all moved to SSD to give you that speed IOPS is what you want to look at. So if my database says I need 3000, I just need a disk, because that will handle all these random reads and write. Okay, so I hope you kind of understood something about on this IO. Is there anything that you may want to know? There is a lot. I mean, sometimes there is I hope you understand there is this sector block and all those kind of stuffs. I hope you understand these. It's your IOPS are directly based on your block sizes and things like that. Okay, so I mean, if I had a way where if I could replace all my hard disk memory with your what is called as real memory or your physical memory, right? I wouldn't be even talking about this topic because everything would be fast, and SSD kind of intends to do that, but it's still not going to be as fast as your real memory is, but it's almost close there. Okay, so that's why you get those performance of 3000 IOPS and things like that, because your storage is fast. Now memory. So memory management is one big module within your kernel, right? And that decides how it handles all the memory to a given application and stuff. So by default, your real memory, that is your physical memory or whatever you want to call it as, or your primary memory, is divided into what are called as pages. Okay, so each page is like 4K in size. Okay, each page is like 4K in size. So so now if you see here, you see this free memory. Okay, you see these buffers. They are all actually in the concept of pages. Okay, whereas yeah, so my total memory is so much. Okay, and use this so much, and yeah, this is so much is kind of free, right? Okay, so what you need to understand is your memories are divided into pages. Okay, now let's understand what these pages mean. Okay, see, to what is it? See, you need to manage your memory, right? When you want to manage your memory, what they do is you can think your memory like your floor tiles. Okay, so these are made of small blocks or 4K in size. So when an application wants some memory to execute, blocks of 4K pages are allocated to an application. Okay, now there is a place in which this entire list is kept about how many pages are there presently. This happens when you actually install and configure your operating system, which happens by default. We don't see it. It keeps a list of how many pages are there for you, and it is from this list, this the command which I ran, free, the free command actually is pulling it out from that. Okay, it gives you the page list from that. So it keeps a list of what I call as pages, and I'll tell you why we are looking at that word page as such. So memory is not allocated to an application in terms of bytes or yeah, or a number of bits or something like that. It is given in form of page, which is around 4K in size. Okay, that's first thing that you need to understand, how the memory is managed. Okay, then we know there is something called swap, right? We all know there is something called swap. And unfortunately, people think swap is a way to increase the performance of your system. Actually, it is not, right? It's just an area on your secondary disk. Okay, it is an area of your secondary disk that helps you to hold your swapped data from your primary memory. So, example, earlier, you know, when the computers were introduced, late 60s, early 70s, memory was very small. It was only 1K, 2K inside, and your operating system, you had to fit into this to run, right? So what they would do is, if my memory was, just say, in MB, Ks or MB, imagine you had a system with 1 MB, right? 1 MB of memory. What is, and if your application was around, say, 2 MB, okay, I'm sure we couldn't fit this application in, right, to execute. So what it would do is, it would load the most required component in the physical memory, and the rest he maps it up, he loads it into the swap area. Okay, he loads it into the swap area. So so then when he requires that, he just swaps the present data from the memory, from the real memory to the physical memory, and that is the secondary memory. And so what was there, the swap comes into the memory, what is in the memory goes back into the swap. So this way, virtual memory management, this is also called as virtual memory management, help you to run applications which are bigger in size than your actual memory is. Okay, and and this way, so there was also another memory called another memory which is called as look-aside buffer. So look-aside buffer is a piece of memory within your physical memory or within your L1 or L2 cache, which holds the mapping of physical memory to swap memory. Okay, so what this says is, in this particular page, I told you physical memory is divided into, in this particular page, data from this area of the swap is loaded. Okay, so that even happens today, because even though we have 16 GB and 32 GB, still there are enough of data that still cannot accommodate. So virtual memory management will take care of that. Now, the other piece of information which you need to know is swap in, swap out. Okay, if you start seeing a lot of activity, that means a lot of numbers which are going, numbers which are changing here towards the high side, that means you are seeing a lot of page faults. Okay, what is a page fault? Accessing the disk will slow your application considerably. Okay, so there are two types of page faults. Soft page faults. When I say what is soft page fault, when a page is found in the memory, okay, but not within the CPU cache. Hard page fault, when the page is not found in the memory. So that means if the page is not found in the memory, it has to be pulled out from the hard disk and put into the memory. it is at that time you may see some swap in happening. But when you start seeing swap out happening, you must consider whether is there some application which is consuming more memory than otherwise it would be required. Okay, so these two fields of swap in and a swap out, we can, I will just run. Okay, I know Edureka may not be in my system. I will run this. Okay, I should have. I should have. I made an error. I should have connected parallelly. 61 dot. This is 39. Okay, it's done through. What we can do is I will start some other word which is not going to be here. Let's say, what word shall I? Okay, so okay, private edu. Okay, something like this, and see, so you see that the first one went fast, and the second one, the first one went slow, and the second one, first one went slow, and the second one went fast, right? And if I do anything like this, it's quickly able to. Why do you think this happened? What happened, which we didn't see? We should have actually seen it. Which we now can't see. All your file system cache. Okay, so you saw this use went up, right? Your file system cache. That is what your file system cache is. There are two types of cache within the file system itself. Okay, I'm sure you know this word called inode, right? Okay, so ls minus il. Okay, okay. So this number is called your inode. Each each application, each file internally is represented by a number, and all these parameters. I hope you are knowing this. Okay, you see all this information. What is my inode? What is my link state? What is my access? What is my UID, GID, access, modify, change? All these parameters are kept in this inode, except for the name of the file. Name of the file is kept in your directory. Okay, so pwd here. I'm in this directory called classes. So so if I do stat on this may not okay, so this is not a file actually, right? How do you know? See, it's a directory. Okay, so the name of these files are kept in this directory. Now what happened is, when I did a find, right, the entire dump of file name and its inode were dumped into the directory. So when I quickly did, when I ran, so when I do now any kind of any search, right, it will just look into the memory. That's why it is going fast. I hope you get some sense of that, right? What we would have seen is, if there was some swap-ins, we would have seen like, or you can copy something and you can see the swap going up and things like that. So you kind of understand what your page faults are, and you understand what is this file system cache. So file system cache is basically your in this so file system cache is that memory in which your file system data, the files are basically kept in your memory for it to become fast for accessing. Okay, then what is this pmap command? Okay, so I can see. Let me check. Okay, my HTTP runs. Should be. Okay, so what this tells you is, see, now how do you do profiling of your application in terms of memory? Okay, this is what you do. The command is called pmap. Okay, I'm sure you must have heard about your RSS. RSS is the resident stay memory used by your thing. Now in this, it shows you what is the starting address of your application. Okay, and it starts from this and it goes on like that. And what it does is it utilizes so much kilobytes of memory. Okay, now in this, stay resident, that RSS is so much, and this is the yeah, where is that? And this so-called dirty is so much. Now what this means is, if you see your PS minus the AF grep HTTPD, you actually see many threads, right? Okay, so this is the total occupied by all these guys. In the main memory, it's so much, and individually per thread it occupies so much. This is the meaning of this, and this is how you calculate per memory, per application, how much memory is utilized. Okay, and if you kind of understand, see, there is anonymous memory is being used here, some stack is being used here, and where you see all this SO, these are all shared memory utilized. Okay, shared memory means this particular library is used by all these threads. Okay, so that is a one-time memory consumption of those shared. Okay, so you see how many now using this you can see my HTTP my web server also loads an LDAP. So if you do a profiling, why the hell I would need to load an LDAP? Because LDAP is not used by application. So this way you can see what get loaded, what is utilized, and you can accordingly remove those modules which are not used. Okay, this way, this is one big way to performance tune your application. So now I see mod Python. Yeah, I may want to use, or mod CGI. I don't think I need to use this because I'm not using any more CGI applications. So you can run through this to understand what modules are loaded. I mean, per application. Okay, this is per application, and you can actually improve the performance. You can clearly come and tell. Now I can tell you, like if you take an HTTP connection per person. Okay, per person. And now imagine I do a connection to, say, of Snapdeal or Flipkart. When I do a connection to say a Flipkart.com, how much of memory? So that means it is the total size of that index page, right? So index page will be 1 MB. Okay, so that means apart from this amount of memory which is utilized by the application, we should look at per user how much memory is allocated. So 1 MB means, so 1 MB we are allocating per user, and I have 1 GB of memory after being utilized by the OS and the application itself. So 1 GB means, so we can nearly have simultaneously 1,000 connections connected to this system. Okay, now if this guy is downloading something, then what happens? The memory which is allocated for him was 1 MB. He may actually start using probably 5 MB and 10 MB. This is where companies limit the utilization of the bandwidth, so that he keeps that constant memory. So from now 1 MB, he may start using maybe some 20 MB, is downloading those applications. Okay, so when you start doing that, the number of simultaneous users who are able to connect also reduces, isn't it? Okay, so that's the way you calculate your memory and your application profiling in terms of your memory. I hope you're getting these things. I know there's a lot of abstract stuff, and this is, these are normally 3-4 day sessions which we run doing, and then we're doing it at a little quicker pace, hoping because you are coming with some experience, and then you can go back and read a little more on this, or probably even send a mail to me. I should be able to answer most of these things. Okay. Okay. So monitoring of memory again. So now what I've noticed, see today the standard way of monitoring through graphical, no server today has any graphs installed. So we all have to go through command line way of monitoring, and command line way of monitoring is always going to be a catch because you can't read everything. So people today, what they do is, to monitor your system, they gather the statistics through various processes, either a cron or maybe you write your own daemon, whatever, and then pull this data into one of the servers and then look it into a graph, maybe across systems, per systems, and things like that. So this is what happens as a part of your DevOps activity. Now you, as a DevOps engineer, should write this entire application of first, what is the command? What is that script you may write? You may write a Perl script, Python script, or a shell script to do a monitoring, to gather statistics of that particular application or device. You write this and you dump this into a file in a continuous process, maybe per minute, per 5 minutes, or however, based on your system load. Okay, and then you would then go back into the monitoring system, write some code to pull this out. Then you have to then merge all this, right? You merge all them probably in a database, and then from the database you create a graph. Okay, so this is one activity as a DevOps you would do: performance gathering, and then taking a decision. And I said earlier it was always done alone. Now you will do it with the dev engineers as well. Okay. Okay, so these ways are kind of a little gone. You can start. We have to use everything through a command line way. Okay. So performance tuning, understanding the problem by reducing it, reproducing it rather. Sorry, try to reproduce the problem, or at least simulate. So we don't really do these things as a DevOps engineer. We would analyze it by gathering your statistics and putting it into a graphical form. Okay, so that's how we start off, and then once we notice any anomalies there, we would then pull in the dev team to analyze it, and that's how we do it. Okay, so we do collect monitor and collect data based on the data. Potential issues can be identified. Eliminate and narrow down issues. Okay, you would do it maybe sometimes on your own, so you know what? Most of the DevOps engineers are also being some kind of developers at some time, so they should understand a bit of these code itself. Okay, and one change at a time. So changing performance is not, you don't do it. You normally have an infrastructure, a test infrastructure to run this whole process. Okay, so how do you tune your CPU? Okay, that's that is something which we really don't do. Okay, we gather the information on CPU statistics. Okay, CPU kernel does not provide any tunable parameters for your CPU subsystem. Okay, we all know that. So the best way to tune your CPU subsystem is know acceptable CPU usage percentages. As I was saying, if a CPU is overutilized through command, and you identify these through commands like top and ping, then you look at finally that process will be moved to another system, or more hardware will be dedicated to the application. These are the only judgments that you can make from a CPU tuning perspective.